Good day everyone! For today's video, we will be talking about Chapter 6 Network Layer, CCNA Routing and Switching, Introduction to Networks. So the main topics or the main points to talk about in this chapter are explain what is network layer. Second, network layer characteristics. Explain how the network layer uses IP protocols for reliable communications. Third, IPv4 packet. Explain the rule of the major header fields in the IPv4 packet. Fourth, IPv6 packet. Explain the rule of the major header fields in the IPv6 packet. Fifth, how a host routes. Explain how network devices using routing tables to direct packets to a destination network. And sixth, routing tables. Explain the function of fields in the routing table of a router. The network layer. The network layer is a portion of online communications that allows for the connection and transfer of data packets between different devices or networks. The network layer is a third level or layer 3 of the Open Systems Interconnection Model or OSI model and the layer that provides data routing paths for network communication. Data is transferred to the receiving device in the form of packets via logical network path in an ordered format controlled by the network layer. What happens at the network layer? Anything that has to do with inter-network connections takes place at the network layer. This includes setting up the routes for data packets to take, checking to see if a server in another network is up and running, and addressing and receiving IP packets from other networks. The last process is the most important, as the vast majority of internet traffic is sent over IP. Network layer characteristics. IP version 4 or IPv4 and IP version 6 or IPv6 are the principal network layer communication protocols. The network layer performs four basic operations. First, addressing end devices. Second, encapsulation. Third, routing. And lastly, the encapsulation. Network layer characteristics. First, addressing end devices. IP addresses must be unique for identification purposes. Second, encapsulation. The protocol data units from the transport layer are encapsulated by adding IP header information including source and destination IP addresses. Third, routing. The network layer provides services to direct packets to other networks. Routers select the best path for a packet to take to its destination network. Fourth, the encapsulation. The destination host encapsulates the packet to see if it matches its own. IP encapsulation. IP encapsulates the transport layer segment. IP can use either IPv4 or IPv6 packet and not impact the layer 4 segment. IP packet will be examined by all layer 3 devices as it traverses the network. And lastly, the IP addressing does not change from source to destination. Characteristics of IP. IP was designed as a protocol with low overhead. It provides only the functions required to deliver a packet from the source to a destination. An IP packet is sent to the destination without prior establishment of a connection. IP was not designed to track and manage the flow of packets. Characteristics of IP is meant to have low overhead and may be described as: first, connectionless; second, best effort; and third, media independent. Connectionless. IP does not establish a connection with the destination before sending the packet. There is no control information needed, synchronizations, acknowledgements, etc. The destination will receive the packet when it arrives, but no pre-notification is sent by IP. If there is a need for connection-oriented traffic, then another protocol will handle this, typically TCP at the transport layer. Best effort. IP will not guarantee delivery of the packet. IP has reduced overhead since there is no mechanism to resend data that is not received. IP does not expect acknowledgements. IP does not know if the other device is operational or if it received the packet. Media independent. IP is unreliable. It cannot manage or fix undelivered or corrupt packets. IP cannot retransmit after an error. IP cannot realign out of sequence packets. IP must rely on other protocols for these functions. IP is media independent. IP does not concern itself with the type of frame required at the data link layer or the media type at the physical layer. IP can be sent over media type, copper, fiber, or wireless. Media independent. The network layer will establish the maximum transmission unit or MTU. The network layer receives this from control information sent by the data link layer. The network layer then establishes the MTU size. Fragmentation is when layer 3 splits the IPv4 packet into smaller units. Fragmenting causes latency. IPv6 does not fragment packets. An example for this one is a router goes from Ethernet to a slow one with a smaller MTU. IPv4 packet. An IPv4 packet header consists of the fields containing binary numbers. These numbers identify various settings of the IP packet which are examined by the layer 3 process. Significant fields include: first, version. It specifies that the packet is IP version 4. Second, differentiated services or depth serve or DS used to determine the priority of each packet on the network. Third, time to leave or TTL limits the lifetime of a packet decrease by 1 at each router along the way. Fourth, protocol used to identify the next level protocol. Fifth, source IPv4 address, source address of the packet. And sixth, destination IPv4 address, address of destination. Limitations of IPv4. IPv4 has been updated to address new challenges. There are 3 major issues that still exist with IPv4. First, IP address depletion. IPv4 has a limited number of unique public IPv4 addresses available. Although there are about 4 billion IPv4 addresses, the exponential growth of new IP-enabled devices has increased the need. Second, internet routing expansion. A routing table contains the routes to different networks in order to make the best path determination. As more devices and servers are connected to the network, more routes are created. A large number of routes can slow down a router. And third, lack of end-to-end connectivity. Network Address Translation, or NAT, was created for devices to share a single IPv4 addresses. However, because they are shared, this can cause problems for technologies that require end-to-end connectivity.
8.3 IPv6 packets. What is IPv6? It is the next generation Internet Protocol, address standard intended to supplement and eventually replace IPv4. Every computer, mobile phone, home automation component, IoT sensor, and any other device connected to the internet needs a numerical IP address. The original IP address scheme, called IPv4, is running out of addresses due to its widespread usage. What is IPv4? IPv4 stands for Internet Protocol version 4. It is the underlying technology that makes it possible for us to connect our devices to the web. Whenever a device accesses the internet, it is assigned to unique numerical IP address. To send data from one computer to another through the web, a data packet must be transferred across the network. Limitations of IPv4. IPv4 has 3 major limitations. First, IPv4 address depletion. We have basically run out of IPv4 addressing. Second, lack of end-to-end connectivity. To make IP4 survive this long, private addressing a network created. This ended direct communications with public addressing. Third, increased network complexity. NAT was meant as temporary solution and creates issues in the network as a side effect as manipulating the network headers addressing. NAT causes latency and troubleshooting issues. IPv6 was developed by Internet Engineering Task Force, or IETF. It overcomes the limitations of IPv4. Improvements that IPv6 provides. It increased address space based on 128-bit address, not 32 bits. Improved packet handling. Simplified the header with fewer fields. It eliminates the need for NAT. Since there is a huge amount of addressing, there is no need to use private addressing internally and be mapped to shared public address. IPv4 packet header fields in the IPv6 packet header. The IPv6 header is simplified but not smaller. The header is fixed at 40 bytes or octets long. Several IPv4 fields were removed to improve performance. Some IPv4 fields were removed to improve performance, flag, fragment offset, and header checksum. IPv6 packet header. Significant fields in the IPv4 header. Functions and its descriptions. Version. This will be for v6 as opposed to v4. A bit field is equals to 0010. Traffic class. Used for COS. Equivalent to diffserv to DS field. Flow label informs device to handle identical flow labels the same way. 20-bit field. Payload length. This 16-bit field indicates the length of the data portion or payload of the IPv6 packet. Next header. IDs. Next level protocol. ICMP, TCP, UDP, and etc. Hop limit. Replaces TTL field layer 3 hop count. Source IPv4 address 128-bit source address. Destination IPv4 address 128-bit destination address. IPv6 packet may also contain extension headers or EH. Extension headers characteristics provide optional network layer information. Are optional, are placed between IPv6 header and the payload, may be used for fragmentation, security, mobility, support, and etc. Note, unlike IPv4, routers do not fragment IPv6 packets. Video sample IPv6 headers in Wireshark. This video will cover the following: IPv6 Ethernet packets in Wireshark, the control information, and the difference between packets. 8.4 How a host routes. Host forwarding decision. Packets are always created at the source. Each host devices creates their own routing table. A host can send packets to the following: itself, the IPv4 or IPv6, local host, destination is on the same LAN, remote host devices are not on the same LAN. The source device determines whether the destination is local or remote. Method of determination: IPv4 source uses its own IP address and subnet mask along with the destination IP address. IPv6 source uses the network address and prefix advertised by the local router. Local traffic is dumped out the host interface to be handled by an intermediary devices. Remote traffic is forwarded directly to the default gateway on the LAN. Default gateway. A router or layer 3 switch can be a default gateway. Features of the default gateway or DGW: it must have an IP address in the same range as the rest of the LAN. It can accept data from the LAN and is capable of forwarding traffic off the LAN. It can route to other networks. If a device has no default gateway or a bad default gateway, its traffic will not be able to leave the LAN. Host routing tables. On Windows, route print or netstat to display the PC routing table. Three sections displayed by these two commands: interface list, all potential interfaces, and MAC addressing. IPv4 routing table and IPv6 routing table. 8.5 Introduction to Routing. Introduction to routing, router packet forward decision. What happens when the router receives the frame from the host device? First, packet arrives on the gigabit Ethernet 0/0/0 interface of router R1. R1 de-encapsulates the layer 2 Ethernet header and trailer. Router R1 examines the destination IPv4 address of the packet and searches for the best match in its IPv4 routing table. The route entry indicates that this packet is forwarded to router 2. Router R1 encapsulates the packet into a new Ethernet header and trailer and forwards the packet to the next hop, router R2. IP router routing table. There are three types of routes in a router's routing table. Directly connected. These routes are automatically added by the router, provided the interface is active and has addressing. Remote. These are the routes the router does not have a direct connection and may be learned manually with a static route, dynamically by using a routing protocol to have the routers share their information with each other. Default route. This forwards all traffic to a specific direction when there is not a match in the routing table. Static routing. Static route characteristics must be configured manually, must be adjusted manually by the administrator when there is a change in the topology. Good for small non-redundant networks, often used in conjunction with a dynamic routing protocol for configuring a default route. Dynamic routing. Dynamic routes automatically discover remote networks, maintain up-to-date information, choose the best path to the destination, find new best paths when there is a topology change. Dynamic routing can also share static default routes with the other routers.